Here's an example of the kind of problem we've been doing. Given a function, in this case x squared minus 1, which gives us a parabola graphed over here, we use the difference quotient formula to find an expression for how to calculate the average rate of change between any 2 points on this graph. So for example, if we picked minus 1 and 2, then the difference quotient formula would give us the slope of the line between the 2 points, which represents its average rate of change between minus 1 and 2. In terms of the formula itself, those 2 points are determined by x and h, where x is the left point and h is the width of the interval that takes us to the right endpoint. So when we find the formula given by the difference quotient, we end up with something that has both an x and an h in it, and that corresponds to the selection of x and h that determine that interval. But we haven't stopped there. After we find the difference quotient formula, we have let h go to 0, which has the effect of shrinking that interval until it has a width of 0. And that leaves us with a single point. At a single point, it's not an average slope anymore. It is an instantaneous slope. And that looks like a tangent line on the graph. A tangent line is a line that just goes in the direction that the graph is going at that one instant, and it touches it at that point we've chosen. The slope of that line is the derivative. We denote the derivative by f prime. If we start with f, then the derivative is f prime. And we get a formula then that no longer has an h in it because the width of the interval has become 0. In order to pull off that mathematical trick of getting rid of the h's, something interesting has to happen in our formula, because the first version of the formula has an h in the bottom. And we can't set h equal to 0 immediately because we'd be dividing by 0. You see, in all these formulas we've got h in the denominator. Still true here. We're simplifying algebraically, and still true here. But at this point, you notice that in the numerator we've also got an h in every term, so we can finally cancel the 1 in the denominator. And that then gives us a formula that we can safely let h go to 0 in. Now mathematically this seems a bit like cheating. How is it that we started with the formula that I can't let h be 0, and I end up with the one that I can let h be 0? And the way mathematicians approach this is with a topic called limits. In the limit, when h goes to 0, we don't actually let h equal 0 because that would violate the principle of not dividing by 0, but we let it get closer and closer and closer. And that process of letting it get closer and closer is called a limit. That's the topic we're going to take up in this video. It's often useful to start with a very simple example to see what's going on. So let's take f of x equals x. This is just a straight line function with slope 1. And if we plug it into our difference quotient formula, we get this familiar looking bit here. We've got f of x plus h, which is just x plus h, minus f of x, which is just x, all over h. And that simplifies very quickly because the x's cancel, and we get just h over h. Now in the past, so far, we would have just happily canceled those h's and said it's equal to 1, and therefore the difference quotient is always 1, and by the way, the derivative is also 1. But technically, if we have a fraction like h over h, we can only say it's equal to 1 if h is not equal to 0, because if h is equal to 0, I have 0 over 0. And that does not cancel out because we can't divide by 0. This is one of those frustrating technical math things that has a good reason behind it. I've sketched for us here the function y equals 1. You can see it's a horizontal line, and it's pretty boring because its value is always y equals 1 all the way across. This is what we would get if we set h over h equals 1. But we have to make an exception for h equals 0, so what we really have is that function with a little hole missing at 0. We often draw a little circle to indicate that the graph omits a point. And so the true graph of h over h is not just the horizontal line 1, it's actually the line 1 with a little hole missing there. What we write mathematically is the limit as h goes to 0 of h over h equals 1. And you can see that left part of the formula there, LIM stands for limit, and then directly underneath it or a little bit off to the side we'll write h and an arrow and 0 to show that h is approaching 0 of h over h. Okay, how to visualize that is think about a little bug walking across the line here. It's happily bebopping along here. A little bug walking toward x equals 0. X equals 0 is where the vertical axis is. As the bug approaches 0, how does its height change, its y value? Does it go above 1 or below 1? No, it doesn't. It always stays right on that line 1. So what we're interested in is how high is the bug as it gets closer and closer to this point that's omitted there, the limit as h goes to 0. We can see that the height is always going to be 1. If we approach from the other end, the bug walks along here, he stays at height 1 the whole time, no matter how close, no matter how much we zoomed in, how close he got to 0, he would always be at height 1. That's what we mean by the limit equals 1. We can talk about limits at other places too. Here's another example. The limit as h goes to 2 of h over h. 2 on my graph would be about maybe right here, right? H equals 2. And if we imagine our bug drooping along until it gets closer and closer to 2 from either direction, the height of the graph, the y value that the bug is experiencing, is always going to stay right at 1 because we're talking about the constant function 1. In this case, the bug could actually get right on the point h equals 2, but that's irrelevant. Whether or not that hole is left out of the graph doesn't matter as far as the limit goes. The limit only cares about what happens a little bit to the left and a little bit to the right. So let's look at a more complicated example. Here, instead of giving a formula for the function, I've just drawn its graph. X is the horizontal axis and y is the vertical axis. And this is the function y equals f of x. We will be asking about limits as x approaches certain numbers for this graph. So the first thing to notice if we just scan the graph is as we go left to right, if I imagine our bug walking along, there's a jump in the graph at x equals -4 right here. And it jumps up 1, 2, 3 units. And the convention is if you draw a solid dot, that means that the function value exists there. So f of -4 is actually 0. And if you draw an open dot, that means it leaves out that point. So all the points right next to -4 to the right of it, x equals -3, x equals -3.99, and so on, they are at this height, which is 3, y equals 3. So then it sails along and then it descends for a little while. Then the function entirely leaves out the point x equals 4 and then goes on its merry way at y equals 0. So let's look at the problem, what happens when x goes to -4. We have to imagine our bug walking along here from the left. What's its height? What's its y value as it approaches -4 from the left? It can't actually get to -4, but we can get as close as we want. And we'd have to conclude that from the left, the bug's height is 0. Now we do the same experiment from the right. Bug's walking along from the right. And now its height is y equals 3. It's 3 units up. The fact that this point with the open circle is omitted has no effect on the limit. The bug can get as close as it wants to -4, but can never actually land on it, according to the rules of the limit. And its height there is 3, y equals 3. So we get 0 from the left and 3 from the right. If we get different answers, we say that the limit itself does not exist. We could be more specific and say why it doesn't exist, because the left limit and the right limit are different, but for now let's just write doesn't exist. Look at the second problem. Now x is approaching 0. What happens to the bug as it approaches 0 from the left and from the right? You might want to stop the video for a moment and see if you can figure that out for yourself. Well, approaching x equals 0 from the left gives us y values consistently at 3, and approaching x equals 0 from the right, you see our bug's climbing up from 1, 2, and eventually gets to the same place. So the limit from the left is 3 and the limit from the right is also 3. So we would say that the limit as x goes to 0 of f of x is 3. Finally, if we turn our attention to the limit as x goes to 4, as we approach 4 from the left, the bug is descending to a height as close as we want to 0. It's never going to get quite to height exactly equals 0, but it'll get closer and closer. And if it approaches from the right instead, it stays at 0. The fact that there's a hole there, that means we cannot exactly land the bug on x equal 4 because it'll fall through the floor and down into a great pit or something. That point simply doesn't exist on the graph, but that does not affect the limit one way or the other because we're not allowed with the limit to land exactly on x equals 4 anyway when we take the limit as x goes to 4. So the left limit in this case is 0 and the right limit is also 0, and so the limit as x goes to 4 of f of x is 0. Here's a function that mathematicians find interesting. It's called the floor function. And it takes any number and rounds it down to the next integer. So it would take 3.2 and round it down to 3. It would take pi and round it down to 3. It never rounds anything up. So it takes negative 0.9 and rounds it down to negative 1, for example. If we graph that, what we get is a stair-step function. At every integer, let's pick 1 here. If you actually put 1 into the function, it's not going to round it down because it's already an integer. And then if you take numbers a little bigger than 1, 1.1, 1.2, and so on, you can see that the y value doesn't change. That's because all of those numbers get rounded down to a height of 1. The output of the function is 1. And that's true all the way up to 1.999999, as many 9s as you want. But as soon as we get to 2, it jumps up to 2, and then the game starts all over again. So that's the floor function. The question for you is, at what points on this function does the limit exist, and at what points does the limit not exist? Think about that for a few minutes and jot down your answer, and then turn the video back on. The answer is that the limit will exist anywhere in the middle of these jumps, because if we approach, say, 1.5, that would be over here. If we approach 1.5 from the left or from the right, our bug's walking along here, and we stay at the same level. We approach the same y value. However, if we picked an integer like, let's say, negative 1, as the bug approaches negative 1 from the left, he'll be 1 unit lower than if he approaches x equals negative 1 from the right. So the limit exists everywhere except at the integers.